Hello guys, it's Johnny time and welcome to another smart contract hacking tutorial. Today we're gonna solve the sixth Damn Vulnerable DeFi challenge, which is the Selfie. So are you ready to level up your smart contract hacking skills? If yes, let's get started. So the exercise name is Selfie, and a new cool lending pool has launched. It's now offering flash loans of DVT tokens. It even includes a fancy governance mechanism to control it. What could go wrong, right? You start with no DVT tokens in balance and the pool has 1.5 million DVT tokens. Your goal is to take them all. So here we're going to combine flash loans with DAO, with governance, and let's start by taking a look at the smart contract. So I'm jumping onto the repository, to the contracts folder, and under Selfie we have three smart contracts. One is the interface, SimpleGovernance. We have the SimpleGovernance, which is probably going to have all the logic for the voting and execution of proposals. And we have Selfie pool. So let's start with the simpler one because we are already familiar with flash loan pools from the previous exercises. So I'm gonna head over to the simple pool smart contract. Now we can see that this contract already inherits some other contracts such as reentry guard, snapshot, ERC20, flash loan lender, flash loan borrower, and we also import the whole simple governance contract. So why? I don't know, maybe just the interface is needed, but in that case, the creator of the challenge decided to import the whole contract. And the contract is inheriting from reentry guard and IRC 3156 flash lender standard. Now we have the snapshot token. So we are using here a ERC20 snapshot token, probably for governance. So we can use the snapshot ID to determine how many votes or what was the token balance on each snapshot, so we can see if proposals are passing or not. This probably we will see more once we go to the governance contract. And here we save in the state of the pool the governance address. It's not an address, it's a simple governance type of data type, but it's actually an address with interface. And here we have the hash for the callback success that we already are familiar with, ERC 3156 flash loan standard. If not, check out my previous walkthroughs where I talk about this flash loan standard. I guess it was the first one, the unstoppable one. And we have 4 errors defined: repay failed, caller not governance, unsupported currency, and callback failed. Now we do have a constructor here, but first we have a modifier only governance. So probably there's going to be an access control to some of the functions which only the governance contract can call. Okay, we'll see it later, and it makes sure that the message sender is governance or it reverts. Now in the constructor we set a token and the governance to basically the state variables. Then we have these two functions that are basically defined by the ARC flash lender standard, which is the max flash loan, is the balance of the pool, and the flash fee is nothing, it's 0, right? So we don't have any fee for the flash loans, and this is our lovely flash loan function. So it allows us to request a flash loan from the pool of DVT tokens. We pass the token, we pass the amount, the receiver is supposed to implement the flash borrower interface, and optional data. Optional, let's see if it's optional, we don't know yet. The token should be the token, the governance token, right? This one. So it should be this snapshot token. This is the only token we can borrow. And then the token is being transferred to the receiver, to who requested the flash loan. And we make the callback on flash loan that is also described in this flash loan standard. And the callback, we send all the data and we make sure that we got the hash, the callback success hash that was defined here. Again, it's part of the standard. Or we revert with callback failed. Also, we validate that we can get the tokens back. We use the transfer from function, which means that the receiver should approve the pool contract to spend this token. If not, this transfer form will fail, and we will revert with repay fail, and we return true. Now here there is another interesting function, emergency exit, which basically can be called only by the governance contract, and it's the external function. We pass an arbitrary parameter, an address of receiver, and then we simply just send all the funds of the pool to this receiver. Now, unfortunately, we are not the governance. The governance is the address of the governance contract. So unless we somehow possess the governance contract, we cannot call this function. If we could easily just get all the money from the pool, but it's not going to be that simple. And now let's jump into the simple governance contract and the interface. So we can already learn some things from the interface. We can see the struct of governance action or proposal. It has a value when it was proposed, executed, a target, an address, probably a smart contract, and the data to pass in the call. So basically we can create some kind of governance proposals that will make the pool execute transaction, which is interesting because if we can make the governance contract to issue a transaction to emergency withdraw the funds from the pool to us, then it's a win, right? Now we have here all the errors defined: not enough votes, cannot execute, invalid target must have a code, action failed, and we raise two events: action queued and action executed. All these functions will be implemented in the governance contract. Now that we have some idea about this contract, let's jump into the code to see how these functions are implemented, right? So we import the snapshot token, then valuable snapshot token. We can also jump to this token to see. It's basically just an ERC20 snapshot standard. So it's just a token with the option to take snapshot and get the balance at a specific snapshot. And here we actually see the first problem, right? Because anyone can take a snapshot. There is no access control. Usually snapshot tokens, there is some kind of access control of which account can create new snapshots. But in this implementation of Damn Valuable Token Snapshot, anyone can take snapshots. So we can already move forward with some audit issue, no access control, and basically anyone can take a snapshot, right? We already found a first issue and we added it to the Damn Valuable Token Snapshot contract. Now, let's see what happens over here. So we have the actions in delay, which is a constant of 2 days, like was described in the description. We have the token address. We have the action counter, which is UN256. So everyone will have a number, a counter, 1, 2, 3, 4. And here we have a mapping that maps between probably action ID or action counter to the actual action, which is the governance action struct, with all the relevant information that we inherit from the interface, this one. So these are the state variables of the governance. And in the construction, we get the token, we set the token, and we start from action counter number 1. So the first action is going to be 1. So what I did here is Command KO, which is basically a shortcut to unfold all the functions. So it's very, very organized. It's very easy to get an overview about the contract and the functions. And here we can see all the functions. And now we can go to every single function and understand what it does. So this is probably to add a new action, to add it to the queue. And this one is to execute it. So we have the delay, right, of 2 days. So we cannot just execute it right away. It needs to be in a queue and then later on be executed. Here we have a function, external pure function to get the action delay. It's pretty simple. It's just going to return the constant. So we can just fold and unfold it and set governance token. Okay. Get the governance token. So these are just getters. So it's very easy. We can just take a look at them, these getters. And here we have these two internal functions. Okay, before we go into the queue action and the execute question, I want to take a look at the logic of these internal functions because they're going to probably be used in this queue action and execute action. So the first one is can be executed. It receives an action ID. It gets the action itself, the struct, and it checks some things. So let's see what it checks. First, it checks that basically, if action to execute dot proposed at equals 0, which means that the action exist. Because if the proposed at is 0, it means that we don't have this action ID, so it just makes sure that the action exists. Now we check the time delta. So the time delta is the current timestamp minus the proposed at when it proposed. So this is the delta of how much time passed between when it was proposed to the current time, and we make sure that it wasn't executed and the time delta is greater than 2 days, greater or equal. So now we know which actions can be executed. They need to exist. The time delay should be more than 2 days, and it shouldn't be executed already, so it can be executed only once. Cool. Has enough votes. Okay, let's see what this does. It gets an address, who, and it gets the balance of the last snapshot. So only in the current snapshot where we have a vote, we get the balance of the account that was passed, and we basically divided the total supply by half. So we get a total supply of the governance token divided by half, and if our balance is greater than the half of the total supply, then we have enough votes. So all we need to do is to get more than half of the supply of the governance token. Cool. Now that we understand these two functions, let's jump into the Q action function, right? So I'm gonna unfold all the functionality one by one, and let's see what we got here. So Q action gets target, value, and data. Basically a smart contract, the value in ETH, and the data that we want to make the call for, I assume. Has enough votes. So we cannot suggest or add the action to the queue if we don't have more than the half supply. We already know what has enough vote done, right? We are the message sender. Now the target cannot be this smart contract, so we cannot basically call the same contract. So every action should have a data, and also the target should have code. So it means that it should be a smart contract. We cannot just make actions and make external calls to EOA accounts without data, because it will revert. We target must have code. Then we get the action ID, which is the action counter. It's going to start with 1, and eventually here we basically increase it. We increment it every new action, and obviously we're going to add this new governance action to the actions mapping together with the action ID, and we emit an event. So in order to make new actions, we need half of the supply. We need the target to be a smart contract. The value could be whatever we want, and the data should be greater than 0. Cool. This is the proposed at, the current timestamp, and executed at is 0 because it wasn't executed yet. Now I assume that the execute action function is going to execute the action, right? Because it just makes sense. It receives an action ID. It's an external payable function. Why it is payable, I don't know, but it's interesting. Okay. Now it makes sure that it can be executed, which we already know what it means. It means that the action exists. It means that basically the time that was passed when it was proposed, it's more than 2 days. And it also means that it wasn't executed already, right? Because probably at the end or here, we will set it to execute it somewhere, I assume. Let's see what happens here. Let's move to the next line, okay? So action to execute, we get it from the mapping. We get the whole action. We update the executed at, right? So in the beginning, we already update that we executed it in this block timestamp, and we emit an event, and then we make an external call from the governance contract, right? It's the call that we wanted to make to the target, right? So we get the target from the action, we get the value from the action, and we get the data from the action. We make sure that it succeeded, and if not, we revert the transaction and we return the data that was returned from the action. Okay, this is super cool, guys. We have a good understanding now about the governance, about the pool, and now let's take a look at the tests file, the state. By the way, if you're already familiar with the state and the contracts, you can move forward in the video to the solution, but I highly recommend you to follow along and to see like how I analyze the contract, how I add audit comments, and how I think basically. Now, let's take a look at a Selfie JavaScript file, and let's see what's going on over here. We have all the accounts and the contracts defined here. We have the constant tokens in pool is 1.5 million. The initial supply is 2 million, which means that if we get all the tokens in the pool, we're already gonna have more than the half of the supply. So we always see where it's going, right? If we're able to get all the tokens in pool and make proposal, it can be executed. Now here we get the signers, we deploy the token, we deploy the governance, we make sure that the first action is one, we deploy the pool, we make sure that the token is right, the governance is right, we transfer the 1.5 million tokens to the pool, and we take the first snapshot, we do some sanity checks, and this is where we need to write our exploitation. And eventually, we should have all the tokens that in the pool, and the pool should have 0 tokens. Now that we understand the objective, we know the contracts, and we understand the state, it's time to activate our attacker mindset, our creativity, and think how we can exploit, how can we write exploitation and exploit this whole protocol. Now, if you find it a bit challenging and you feel that you lack some basic knowledge about DAOs, about flash loans, and you want to solidify your skills in smart contract hacking and auditing, I highly recommend you to check out the complete smart contract hacking course, where we are going to cover so many chapters together, and everyone comes with hands-on exercises like this one with walkthroughs and awesome guest lectures by the most crazy professionals from the industry. Now, another advantage is that you get access to an exclusive Discord community with all the students, with myself, with the other teachers, where you can ask questions, where you can meet people, get new opportunities, job opportunities, contest opportunities, and you're gonna basically join the journey together with other people, which is awesome. And obviously, by the end of the course, you will have a final exam and you will get an official certification that will help you to showcase your skills and increase your chances of getting a smart contract auditor position in an auditing firm or blockchain company. Now, if this is something that you might be interested in, get a special link in the description below to receive $100 limited time discount to get all of this. It's a huge course, a lot of value, a lot of materials, community, certificate, everything all included. Use the link in the description below. All right, it's time to write our exploit and exploit the governance mechanism. And the first thing I'm going to do is create a new smart contract in the player contracts folder and call it attack Selfie.sol. Right? Why do we need contract for this scenario? Is because it's going to involve flash loans, and we need to implement the callback function to receive the tokens and create a proposal. So we need to create a contract, right? So I'm just going to copy from previous exercise, just this line of code, right? So let's just copy the Solidity Pragma and contract. Let's call it attack Selfie. Right, now we have the contract set, and let's try to think what we need to do. First, we need to request a flash loan of all the tokens. This is step one, right? We want to get all the 1.5 million tokens from the pool. Now, once we have half of the supply, more than half of the supply, we want to basically add to the queue a new action, right? Now, what this action is going to be, this action should be calling the function, right? We want to call from the governance, the Selfie pool, we want to call the emergency exit function. So we want to call this function, the action, let's add it to our pseudocode over here. So the action will be this emergency exit, and the receiver should be the player account, right? We need to be the ones who receive all the emergency exit juicy funds. Now, once we added the queue to the action, the third step would be to pay back the loan, right? Because we already don't need the supply. We use it to add an action to the queue. We saw that it's necessary to add an action to the queue, and the execution, it's not necessary. The execution just make sure that it wasn't executed and the time has passed. Then, right, we want to wait 2 days. We don't really need to wait 2 days. We can move the time forward in harder to simulate the scenarios, but we have to, if it was a real life scenario, then we would have to wait 2 days in order to execute the action, and then we want to execute the action, and voila, the action will be executed. The call will be made from the governance to the pool, and we will get all the tokens through the emergency exit function. Easy peasy, right? Let's start with the constructor. So the constructor, we want to work with several smart contracts. That's why we need to send all the contracts addresses in the constructor. So it will be the pool. So it will be address pool. We will need to use it to request a flash loan from the pool. We want the address of the governance to make to queue questions and maybe execute them. So it will be governance. We want also the address of the token, the governance token, and we want, that's it. I think that's enough. That should be enough. So we will also define here an address immutable. Let's call it player. This is our malicious EOA account, and we will set the player equals message.sender. So we will eventually send, we will do some checks with the player. The emergency exit should be sending the money to the player. So we'll have his address. And let's define here also interfaces for the pool. So interface, the name will be iPool. And we will add the functionalities later. Also interface for the governance, iGovernance, and we will add it later, right? And now we can define those state variables. So I will do something like iPool, immutable, and we will call it pool. And let's do also iGovernance, immutable, governance. Awesome. We also want to set a token. So for the token, I'm going to use the interface for IERC20, and I'm also going to use the flash loan borrower because we need to implement this callback function to receive the funds from the pool. So I will define over here IERC interface for IERC20 snapshot, right? Because we want to extend the functionality of this IERC20. So I will do is IERC20, and we need some extra functionality to call the snapshot function because we want to make a new snapshot before we make our new proposal. So I will just write here function snapshot. And let's see what it actually gets. So we can go to the Damn Valuable token snapshot, and it basically, this function, I can just copy it. So I will do something like this. It should be external, and it returns the last snapshot ID. So now we can basically set a state variable of IERC20 snapshot. It will also be immutable, and it will be the token, right? Now we can set all these parameters in the constructor. So the pool will be equals iPool, and with the pool address. Then the governance will be governance equals iGovernance with the address. And the token will be token equals IERC token snapshot with the token address. Awesome. We have our constructor. We didn't write the interface for the functions because we still are not sure of what functions we need to use. And now let's define our attack function. So it will be function attack, and it will be external. This is our attack function, right? And what do we need to do first to initiate our attack, guys? I want you to think, right? So the first thing we want to do is to request the tokens from the pool to make a flash loan. So we will use this flash loan function, and I will copy it for our interface of the pool. So this will be basically the function. I can remove the modifier. Yeah, this is the interface for the flash loan. And now we can call the flash loan function. So I will do something like pool.flashloan. And we now have all the parameters. So the receiver is, who is going to be the receiver? This smart contract. So we will need to wrap it with the interface of the flash loan borrower. So I will do something like this, and it will be address of this smart contract. Let's break the line so it will be cleaner. And this is going to be the receiver, the token. We have the address of the token, the amount, how many tokens we want to get from the pool, guys. We want to get all the money of the pool, so we can simply request it, but we already know it. It's going to be 1.5 million. So it will be 1, 5, 1, 2, 3. We can actually do something like this. So it will be 1, 5, 0, 0, and 0, 0, 0. So it will be more readable. So we're going to request $1.5 million or tokens, and the data, we don't need to pass any data to the flash loan function. So we're gonna just pass empty data just like that. Now we will request a flash loan, and as we know already, it's gonna make a callback on flash loan. So we need to implement this function, right? So this one right here, I'm just gonna copy here, and we'll define a new function on flash loan. It will be external, and we will make some access control over here. I can actually copy it from the previous exercise. I think it was here, side entrance. Yeah, these two lines of code just gonna make sure, if you didn't watch my previous exercise, previous solution, check it out. So it's gonna make sure that the TX origin is player. So I am the one who initiated the attack and no one else. And the caller is the pool, right? The flash loan pool. So no one else is able to call this flash loan function apart from the pool. Now, what parameters will receive message sender? So it will be address, and it will be flash loan issuer. Let's do it something like this. Or issuer, right? Issuer or executor. I don't know how to call it. Like the one who executed the flash loan. So initiator, right? The token is just going to be the address of the token. This will be uint, I guess. Let's see. Yeah. We can see it actually here in the interface of the iFlashLoan borrower, but I think it's uint 256, and this will be the amount, and this is gonna be, this is gonna be bytes memory data. This will be the data, and there you go. We have the callback set, and now we need to think what we want to do with these tokens. We got a 1.5 million tokens. What do we want to do? The first thing we want to do is take a new snapshot of the token. Make sure we have a new snapshot and we have all the supplies. So we're going to do token.snapshot, right? So we are taking a new snapshot. Now, once we took the snapshot, we want to queue a new action, add a new action to the queue. So I'm going to copy it and add it to our nice interface over here. And we need a target. We need the value and the data. Now, the target is going to be the pool contract, right? So the target is the pool contract. The value could be 0 because we don't need any ETH. We just need to make the pool, to call the pool a function from the governance. Now, which functions we want to call? We need to encode it into the data. We want to call the emergency exit together with the receiver, which is the player account, right? We want to call the emergency exit function and get all the funds to the player account. So let's first define the data. The data is going to be bytes memory. We need to encode it into bytes, and we're going to use let's call it data. And we're going to use the ABI.encode with signature, right? We're going to use the signature of the string and the arguments of the functions. So the string is going to be the function, basically name and the parameter that it receives, which is going to be emergency exit with address. So it will be emergency exit that receives an address and the argument that we want to set, who is the address that we want to do the emergency exit with? It's going to be the player account, right? So we are encoding this whole thing into the data. It will be bytes, and we will pass it to the action. Now we can just do something like governance.queueAction, and the target is going to be the address of the pool. The value is going to be 0, and the data is just going to be the data. So we are basically adding a new action to the queue to call the pool and call this function with this parameter. Beautiful, simple, clear, and clean. Now, the only thing we have left to do is to pay back the money and return the right hash for the pool, because we still have the tokens. We need to pay them back. So we don't transfer them. We just need to approve the pool to spend our token and return this hash, right? So we make sure to return this hash. So we're first going to approve the pool to spend the token so it can take it back from us. So we'll do token.approve, and the spender will be the address of the pool. The amount will be 1.5 million tokens. We can actually use a constant, but I'm too lazy. So that's it. And we need to return the hash. So we'll return something like kekak256, and the hash should be, we can just copy it from the callback, this one. We're just gonna return the same hash, right? So the pool will be happy. So we'll do something like this. I can just remove this. And that's supposed to be it, right? What's the issue? Yeah, the issue is we didn't define here that we return bytes. So I'll do something like returns, and it will be bytes 32. So we are returning 32 bytes. So the flash loan function will be happy, right? We can actually also change this to call data. So yeah. Awesome. This is our contract that's supposed to be able to add a malicious queue action to the queue through the flash loan. Now we cannot execute the flash loan yet because we need to make sure that 2 days pass. So it cannot happen in the same transaction. We need to wait 2 days and only later call the execute function. That's where comes our JavaScript code. Let's go to our JavaScript code. And the first thing we want to do is deploy our malicious attack contract. So this.attack contract equals await and another await. We're gonna use the ithers.get contract factory function. The contract name is attack selfie indeed. And we're gonna deploy it with a player account, and we will call the deploy function. And now we need to pass all the parameters to the constructor in the right order. So it should be first the pool, governance, and token address. So let's start with pool.address, and then governance.address, and then token.address. Awesome, we deployed our malicious contract. Now it's time to call the attack function, this .attack contract.attack, which will initiate this whole beautiful attack that we just implemented over here. And now that we added the question, the new action through the attack, we need to move the time forward because we don't want to wait 2 days. We can use these hardened network helpers in order to basically push the time forward and simulate like time passes in our blockchain, local simulated blockchain. So let's make a new const action delay, because we don't have it either defined, but we do have it in the contract. The action delay should be 2 days. So we will do something like that. We will do 2 days multiplied by 24. It's going to be in seconds, right? So it needs to be 2 days by 24 hours by 60 minutes in 1 hour, right? And we have also 60 seconds in 1 minute. And we're just gonna add one just in case. You know, I always like to add one just in case to make sure that more than 2 days passed. And we will do await time.increase. And we will gonna increase the time with the action delay, because we can use this time imported library from the hardened network helpers, and we are basically moving the time forward. We also did, I think, something similar here, or if not, we got it here in the time import. So we are moving the time forward, and now that we are past 2 days, we can execute the governance action. So we'll do await governance.connect. We are basically connecting our player account to make sure that the transaction will be sent with our attacker account, and execute action. Now we know that there are any new actions made to the governance, so it still should be action number 1. This is going to be the ID. So I'm just going to pass outcoded one parameter. And I think this should be enough, right? We deploy our malicious contract, flash loan, queue action with the emergency withdrawal to our player account. This is going to be happening in the attack function. We push the time forward 2 days and 1 second, and we execute the action, which should make eventually this call here. This call to get this emergency withdrawal function, get the funds to our player account. All right, guys, so I tried to run the exploit and I had 2 issues. First, the amount wasn't correct. I used 1.5 million WE, and I need to use Ether because the governance token is with 18 decimal numbers, so it wasn't enough votes. So I basically made a constant amount, and I just defined here 1.5 million with 18 decimal numbers, and I passed it here to the flash loan request, and also I passed this same amount instead of running it twice. It would make more sense to approve, so we can pay back the flash loan. This was one issue. And the second issue that the onFlashLoan function wasn't exactly the same like we had here on the pool, because there was another uint parameter, which is the value of the flash loan, the value in ETH, which is 0. So basically, the SIG hash didn't match. So I had to add here another uint256, and I also removed the variable names because I don't use them at all. So I can just define the types. And now everything looks okay. And now it's time to try and run our exploits. So I'm gonna go to my command line and yarn selfie, and let's cross our fingers. And congratulations, guys, you were able to hack the governance mechanism to take a flash loan of all the tokens in the pool, make a new action in the governance, a queued action, pay back the tokens, and execute this malicious action to call the emergency withdrawal function with your malicious account to get all the tokens from the pool. You completed the 6th Damn Vulnerable DeFi challenge. And if you enjoyed this video, make sure to smash the like button and subscribe to the channel for more awesome smart contract hacking videos that will be published in the future. Any questions? Ask them in the comments below. Thank you so much, and I will see you in the next time. Bye bye.